Bismillahirrahmanirrahim. Start with the name of Allah, the most gracious and the most merciful. My name is Isha Shafiq and I am from the Department of BS Chemistry. The topic of my presentation is Ultimate Tensile Strength, short for UTS. And today I am going to discuss what is Introduction to Ultimate Tensile Strength, science and physics behind Ultimate Tensile Strength, tensile test, real world UTS values, influence of structure and processing, modern and advanced strengths, applications of UTS and the summary of UTS. So let's start it. Ultimate tensile strength. Ultimate tensile strength is the maximum stress that a material can withstand while being stretched or pulled out before it breaks or fractures. It represents the peak load bearing or carrying capacity of a material under tension. Formula: UTS is equals to F max over A naught, where F max is equals to maximum load and applied before fracture, and A naught is equals to original cross section area of the specimen in mm square, which is millimeter square or meter square. As a unit, UTS is equals to Newton per meter square or Pascal, commonly expressed as megapascals. Graphical representations: in a stress strain curve, elastic region stress is directly proportional to strain, which is Hooke's law. Yield point include plastic deformation begins, where plastic deformation begins, UTS point where maximum stress attained, fracture point where material breaks. On a stress strain curve, the UTS correspond to the highest point of the curve before necking begins. You can see in the picture. It indicates the transformation from uniform deformation to localized deformation, which is necking. Typical UTS values are given below in the table. Mild steel, stainless steel, aluminum alloy, copper and nylon values are given. Atomic region of UTS. UTS is the microscopic manifestation of how atomic bonds and the microstructure defects that modify them resist separation and sliding under tensile load. At the atomic scale, the competition is between bond rupture and defect mediated plasticity that relieves stress before bond must break out. Science and physics behind UTS: metals, metallic bonding, dislocations and collective plasticity. Metallic bonds are non-directional with a sea of localized electrons. Atoms occupy lattice C and yield by dislocation motion along crystallographic slip system. The macroscopic UTS reflects the peak flow stress reached when work hardening no longer compensates strain localization. Work hardening arises from increasing dislocation density and interaction. Next, relations. The Taylor or dislocation scaling mechanical is given below. The Koch making storage recovery is also given below. Mechanism that rise UTS. Increasing dislocation density, grain refinement, Hall patch, solid solution, strengthening, precipitation, hardening. Recent micropillar and bulk studies quantify how GNDs and dislocation array control strain hardening and UTS in widely used alloys. Ceramics. Ionic bonds or covalent bonds are strong and directional. Crystals have limited dislocation mobility at room temperature, so plasticity is small. Failure typically occur by cleavage, grain boundary separation or micro crack collapses, i.e. brittle fracture. Thus measured UTS can be high, megapascal to gigapascal, but apparently the strength is extremely flux sensitive. The fracture mechanism, the LEFM relation for fracture from a flaw is given below. Toughening mechanism that improve UTS in practice: grain bridging, microcrack, deflection, transformation, toughening, and fiber reinforcement. Microstructural engineering routes summarized in 2023 to 2025 reviews and that show how these mechanisms increase effective UTS or toughness in advanced ceramics and ceramic matrix composites. Polymers. Polymer strength depend on chain backbone, covalent bond, interchain entanglement and secondary interactions. Under tension, Polymer show chain orientation, chain pullout, disentanglement, grazing, and eventually chain scissions. These mechanisms set UTS 10 second to 10 100 second megapascals. For engineering polymer, much higher for oriented or high MW fibers. Next point is micro mechanism. Entanglement act like transient cross-link tensile loading causes chain alignment and load transfer through entanglements. Crazies are networks that are networks of fibrils that absorb large energy that they delay catastrophic crack propagation and raise apparent toughness and UTS when present. UTS recent reviews and modeling quantify how molecular weight, branching, and short chain additives change entanglement in density and tensile responses. Quantitative points, the molecular parameter correlate directly with plateau modulus and with the ability of the network to transmit tensile stress, altering shift yield of or UTS markedly. Next point is, this is the difference between metals, ceramics, polymers, and composites. Their primary bonds, UTS range, and microscopic mechanisms are given in this picture. Next point is composites. Composites are high strength fibers embedded in a matrix. Atomic bonding is hybrid. Strong covalent or graphitic bonding in fibers, weaker interfacial adhesion with the matrix. UTS of the composite depend less on the matrix bond length strength than on fiber strength, fiber volume fraction, orientation, and fiber matrix over interface. Dominant microscopic failure modes: fiber fracture, fiber matrix debonding, fiber pullout and matrix cracking, fiber pullout and fiber frictional sliding, extract and increase composite toughness and effective UTS. Recent 2023 to 2024 experiment work specifically quantifies interfacial shear strength via single fiber pullout test and link interface chemistry to pull out energy and composite UTS. Next point is cross-cutting. Quantitative relations, theoretical or ideal strength versus observed strength. Ideal strength is approximately order of magnitude. Real world UTS is less than theoretical due to the defects dislocation. Recent paper showed that this gap quantitatively across metals and ceramics. Hall patch equation for metals and fracture from a crack is given below. Dislocation theory for metals. Dislocation plasticity in metals. In metallic crystals, plastic deformation chiefly occur via the motion of dislocation on slip system. When a shear stress is applied, dislocation glide under the resolved shear stress and lead to the permanent irreversible deformation. Because dislocation can multiply, interact, and can be hindered by various obstacles, the strength and work hardening behavior of metals are fundamentally controlled by dislocation mechanics. Grain boundary strengthening Hall patch relation. The Hall patch relation expresses the phenomenon that smaller grains, i.e., more grain boundaries per volume, lead to higher yield strength. The relation is that grain boundaries are act as obstacles to dislocation motion, and dislocation pile up at boundaries, requiring higher stress for further motion or transmission across the boundary. That is given below. Recent work continues to evaluate and define the Hall patch equation for behavior in advanced alloys. For example, a 2023 study by Dengwall et al. Showed that in ultrafine regained materials processed by severe plastic deformation, deviation from the classical Hall patch trend appear when grain sizes are reduced to approximately 70 to 150 nanometer. They observed an upbreak or strengthening beyond the expected slope above approximately 500 to 1000 nanometer, followed by a down peak. Next point is it is shown in this diagram. Grain boundaries, wait, dislocation motion and the grain boundaries, and this is the Hall-Petch equation. Mechanistic explanation from the dislocation point of view. When a dislocation moves and encounters a grain boundary, it cannot easily continue in the adjacent grain unless the boundary yields or the dislocation transmits or nucleates a new dislocation on the other side. The accumulation of a pileup at the boundary increases local stress. If that stress reaches a critical value, transmission occurs for a new dislocation is generated in the adjacent grain. Smaller grain reduce the length of pileups and the stress required to move dislocation increases, hence the grain size strengthening. Precipitation hardening. Precipitation hardening is a very strong strengthening mechanism in many alloys. For example, aluminium, nickel, cobalt, copper-based alloys. Merging steels. Fine precipitate act as obstacles to dislocation motion either by shearing the particle or by Odovan looping, depending on precipitate size and depending on the precipitate size. Wait. Coherency, spacing, and matrix or precipitate mismatch. Work hardening. Work hardening refers to a phenomenon that during plastic deformation, dislocation multiply, tangle, and increase the internal stress field and force dislocation obstacles, leading to increased flow stress, or as strain increase, the increased dislocation density rho causes an increment in strength of the form. Taylor hardening, which is given below. The recent literature continues to highlight the role of dislocation substructure and dislocation density evolution in determining mechanical properties. Next point is covalent and ionic materials. Covalent and ionic materials, ceramic and semiconductors. In materials dominated by ionic or covalent bonding, which is ceramic like Al2O3, aluminum oxide, and silicon carbonate, the deformation behavior is very different from metals because slip by dislocation motion is severely restricted. High lattice few active slip system, high lattice resistance, and strong directional bond. The primary deformation mode is bond breakage and fracture rather than plastic flow. Mechanism of deformation and failure. In covalent or ionic crystals, atoms are strongly bonded. Dislocation is difficult because high pure narrow stress few slip system, that is large bond energies emitted, limited dislocation mobility or consequently, when load is applied rather than slip, the bond breaks, cracks, nucleate, and propagate. Therefore, these materials often exhibit very high ultimate tensile strength or compressive strength, but very low plastic deformation, i.e., brittle behavior. Next point is grain size and flaw control. One Hall-Petch analog exists in ceramic: small grain size, small flaws, higher strength. But the mechanism is different. It is largely due to the reducing crack initiating flaws, not dislocation pileup. For ceramics, semiconductors, controlling defects is more beneficial than relying on dislocation strengthening. Practical considerations: ceramic or ionic materials are used where high stiffness or high temperature performance or chemical stability is needed, not necessary ductility. Engineering design must accommodate the brittle nature, minimal plastic deformation, conservative safety factors, and careful flaws detections. Next point is mechanism of strengthening in polymer and biopolymer. Key factors influencing strength in polymers include include chain length. Longer chain create more entanglements, higher strength and toughness, crystallinity, semi-crystalline. Polymers show higher stiffness and strength. Crystallites act as physical crosslinking. Chemical crosslinks restrict chain mobility, increase strength and modulus, but less may reduce ductility. Hydrogen bonding or secondary interaction. Biopolymers such as PVA or the starch rely on hydrogen bond between chains. More bonding increases intermolecular strength. Nanofiller reinforcement. The addition of nanoscale fillers increases modulus and strength by load transfer, restricting polymer and chain mobility and interrupting crack propagation. Nanofillers and bioplastic strengthening. Specifically, nanofillers with high aspect ratio provide pathways for stress transfer and hinder crack propagation. The interface between filler and matrix is critical. Good dispersion and interfacial adhesions are required. The optimum fillers content exists. Plasticizers may improve ductility but often at cost of strength and modulus. Next point is comparison with metals. Metals dislocation, slips, plastic deformation, work hardening and significant ductility and toughness. For polymers, chain mobility, entanglement and filler reinforcements are limited plasticity, different failure modes. Strengthening plastic tactics differs. In metals, you hinder dislocations. In polymer, you hinder restrict chains and reinforce the matrix. Practical implementation. For bioplastic, mechanical performance is strongly dependent on molecular weight, crystallinity, filler type and dispersion and processing conditions. For sustainable materials, combining renewable biopolymer with nanofillers offers a route to higher strength and functional properties, but require optimization of filler matrix interface and processing. For a materials engineering assignment, when comparing with metals, strengthening highlights that while metals rely on dislocation mechanics, polymers rely on chain matrix and interfacial physics. Tensile test, which is the third point. The uniaxial test is the most fundamental mechanical test for quantifying the tensile response of materials. It yields primarily on engineering properties used in material selection, design, finite element, constitutive model calibration, quality control, and failure analysis. Young modulus, yield strength, ultimate tensile strength, elongation at peak, at break, reduction of area, work hardening behavior, and the test is standardized to ensure inner laboratory compatibility. Commonly used standards include ASTM E8 or E8M for metals and ASTM D638 for plastics. Conditioning and environment. Standard requirement and humidity control testing, room temperature range and conditioning time specified. Both polymer and metals can be sensitive to environmental conditions. For polymers, moisture uptake to and thermal history drastically changes stiffness and ductility. ASTM D638 includes conditioning recommendation. Next point is machine and instrumentation. UTM, Universal Testing Machine. A UTM consists of a load frame with a precise calibrated load cell, platens or grip to transmit axial load, and a displacement actuated load capacity and stiffness must be selected to minimize machine compliance and to cover the expected maximum force safely. QA include periodic calibration traceable to standards, displacement and strain measurement. Broad approach is used as cross-head displacement, simple but include machine compliance and grip slippage, acceptable for crude indicator only. Gauge extensomer, clip-on extensomer measure gauge length extension directly and is standard for precise modulus and yield determination. Extensomers can be mechanical, clip-on or contactless, laser or optical. Next point is test procedures. Test procedures are many test procedures. Measure specimen geometry precisely, LO or L0, width, thickness or diameter using calibrated micrometers. For rectangular specimen, A0 is equals to width multiplied by thickness. For round, A0 is equals to pi d square by 4. Mount specimen with alignment of wide bending ensure grips are tightened, but standard torque using hydraulic pneumatic grips for ductile wedge grips for many plastics. Displacement and measurement. Broad approaches used are chord equations. Engineering measures the engineering stress is given below. Engineering strain is also given below, where L length del L is divided by L naught, which is L minus L naught over L naught. Engineering stress strain is convenient for material performance and reporting and is UTS and is standard output of many UTMs. True measure pre-necking. When deformation is uniform, assume volume conservation. Engineering and true measures relate as follows. Necking. What is necking? Onset of necking. In uniaxial tensile test of ductile metals, the transition from uniform elongation to localized necking occurs when the increase of true stress with true strain can no longer compensate for the reduction in load carrying area. The classical considered equation for onset of localized necking is given below, where you can see the post necking elongation is this point and the uniform elongation, yield strength, ultimate tensile strength points you can see there. True versus engineering UTS and the illusion of strength drop. In engineering stress strain curve, the maximum UTS occur at the point where the load reaches its maximum because the plotted stress uses original areas. Once a local neck forms, engineering stress drop if the actual true stress strain continues to rise. This is why conversion to true stress strain or measurement of local with DC or local cross-section measurement is essential to study material hardening to large strains. Post-necking. True stress extraction and Bridgman correction. Extracting a representative true stress strain curve beyond necking requires either direct measurement of the instantaneous minimum cross-section or implication of analytical correction that analytical corrections that account for the triaxial stress state in the neck. Data analysis and drive properties. Elastic modulus. Evaluate as the slope of engineering stress versus engineering strain in the initial linear portion using extensometer data and linear regression over the appropriate strain level as strain interval as specified in standards. Yield point can be defined as via offset method, proportionality limit, or by more sophisticated construction in material with yield point phenomenon. Standard common use the value the 0.2% offset to define sigma y, which is when no clear yield plateau exists, strain hardening component of the fitting fit true stress versus true plastic strain data in a chosen strain window to Holman or other models report K and N fitting ranges, report goodness of fit and comment about deviations at low high strain or due to transformation, for example trip or twip steels. Elongation and reduction areas, percentage elongation, where LF is the final gauge length after fractures. Reduction of areas, where AF is minimal cross-section area of fracture, gauge length and gauge width choice. Effect EL, so report specimen type and gauge after and gauge length per standard. These are the real world values for different materials. Their ultimate tensile strength, yield strength and elongations are given in this table. Stainless steel 3.304. Typical sources of values often show 304 in the approximately 500 to 620 megapascal UTS range for annealed material used. Values of 600 to 750 megapascals usually reflect cold worked or strain hardened product forms or specific testing. Orientation, cross corrosion resistance come from austenitic microstructure. Strain hardening increases UTS sustainability. Titanium alloy Ti6 aluminum and V4V. Ti6Al and 4V is a two-phase alpha plus beta titanium alloy with a stronger alpha stabilizer, which is aluminum, and beta stabilizer vanadium, that provide a high strength weight ratio. Processing and heat treatment produce UTS from approximately 900 megapascal to up to and above 1100 megapascals in some conditions. Carbon fiber composites 350 to 600 3500 to 6000 megapascals. Clarification: the quoted range correspond to fiber tensile strength. As manufactured high modulus or high strength carbon fibers show single fiber tensile strength in the GPA range. A unidirectional CFRP laminate longitudinal UTS can be in the flow GPA range for continuous high volume fraction well aligned fiber, but composite laminate strength is dramatically influenced by fiber volume fraction, fiber orientation and metrics and test method. Recent reviews summarize CFRP tensile performance and design level values. Human cortical bone, approximately 130 megapascals. Human cortical bone is a hierarchically structured mineralized collagen composite in tension. Macroscopic cortical bone typically fails at approximately 100 to 150 megapascals depending on orientation, age and hydration and anatomical site. Biological scatter and anisotropy are major caveats. Report mean approximately plus minus ST when possible. Nylon 66 80 to 150 megapascals. Injection molded unreinforced nylon 6 by 6 typical nylon 66 typical tensile strength fall in the 80 to 150 window. Data sheets and manufacturer technical data provide these typical values and test conditions. ASTM D638 for plastics. These are the values of different compounds and their tensile strength and their hardnesses. Moving on to next point. Phase stability and transformation. Elevated temperature uh, can change phase friction, altering strength. Matrix softening in polymer viscoelastic material approaching glass transition drastically reduces modular strength. Semicrystalline polymers soften as crystalline lamella and lose stability. Dynamic strain, aging, or low temperature embrittlement in some alloy can produce monotonic T dependence. Strength peak at temperature at intermediate strength peak at intermediate temperature. Strain rate. Physical mechanism. Rate sensitivity. At higher strain rate, deformation is faster than thermally activated relaxation process, producing higher flow stresses and increased apparent UTS. Rate sensitivity is more pronounced in materials where plasticity is dislocation controlled or governed by thermally activated chain mobility. Adiabatic heating at very high rates. Local heating may soften the material, partially contracting rate, strengthening micromechanical effect in composite. Strain rate may change fracture mode, causing different UTS responses. Crystallinity in polymer mechanism. Crystalline fraction and lamellar morphology. Higher crystallinity increase load bearing crystalline domain, which increases or raise modulus and yield or UTS by resisting chain pullouts. Tie molecules and amorphous phase. Mechanical toughness still depend on the amorphous region and entanglement. Overly high crystallinity and reduced toughness and impact strength while increasing UTS. Reinforcement mechanism. Load transfer fibers or rigid nanoparticles carry load if they are well bonded to the matrix. Effective stress transfer increased composite UTS. Grain refinement and Orwan strengthening. Nanoscale particles inhibit dislocation. Motion Orwan and loop define grain. Zener pinning and promote precipitation hardening and increasing UTS. Interface quality. The reinforcement effect depends critically on interface adhesion, dispersion, and volume fraction. Poor dispersion or weak interface can reduce UTS or reduce ductility. Heat treatment mechanism. Heat treatment alter the size distribution and coherency of precipitate, dislocation density, and grain size and phase fraction, all of which directly control UTS. Typically strengthening mechanism are precipitation hardening, martensitic transformation and tempering, and solid solution strengthening and grain growth, which may lower strength. Additive manufacturing. Layer beyond UTS and interlayer bonding and UTS. Mechanism. In extrusion based AM, FDM, FF or FFF, and many layer by layer processes, interlayered interfaces are often the weakest part. Interlayer diffusion, entanglement, or metallurgical fusion determine the effective UTS in the build direction. Parameters influencing interlayering: bonding, nozzle temperature, laser powered layer thickness, fuel feed rate or scan speed, substrate temperature, dwell time, and in situ energy density. Poor interlayer diffusion leads to anisotropy, much lower UTS normal to the layer. Practical guidance for AM counterparts. For AM parts where UTS is critical, optimize process window that maximize interlayer temperature and dwell time consistent with dimensional control. Increase nozzle or layer energy speed energy, reduce print speed, and use heated built chambers to promote diffusion or entanglement, employ post print annealing or hot isostatic pressing when possible. Always test UTS in both transverse and transverse direction and report anisotropy. Next point is modern and advanced trends. High entropy alloy. High entropy alloy or HEA are multi-principal element alloy that form simple solid solution phases. HEAs gained traction because configurational entropy stabilizes single phases and produce novel mechanisms of strengthening and damaging tolerance not available in traditional binary alloy. HEA tailored to obtain UTS approaching or exceeding 1 to 1.5 GPa or gigapascal while retaining the useful ductility in some cases, opening prospects for structural application where weight and toughness are critical. For example, equiatomic cobalt, chromium, iron, manganese, and nickel and related derivatives continue to be intensively studied for processing microstructure properties and relationships. Next point is representative UTS numbers and experimental demonstration. Several studies demonstrate that properly processed COCR, Fe, M, and Ni family alloy, especially when combined with grain refinement, precipitation, and phase engineering, can reach UTS values on the order of 1.0 gigapascal, and in some engineered compositions exceed 1.2 GPas while maintaining non-trivial uniform elongation. These high strength are often achieved by thermomechanical processing, cryo rolling, or additive manufacturing, followed by post processing. Next point is nano-architectured materials. What are nano-architectured materials? Nano-architectured materials are engineered solid by whose mechanical behavior is dominated by geometry at micro to nanoscale rather than by bulk composition alone. Using 2-photon lithography, projection lithography, or nanoscale 3D printing, researchers fabricated micro lattices and truss architectures with feature sizes down to 100 of nanometers, 100 s of nanometers, and relative densities well below 1 gram per centimeter cubed. Several recent works shows UTS values exceeding 1 GPa for certain ceramic or pyrolytic carbon nanolattices after pyrolysis of or for metallic nanolithic for with very high strength, with very high specific strength. Next point is bio-based composites. Context and motivation, environmental pressures, and circularity goal have driven research into bio-based polymer and composites and as alternatives to petroleum-derived plastic. The last 3 years show substantial improvement in tensile properties of biofilm via incorporation of lignin, nanocellulose, and chitosan, sometimes yielding 2 to 5 times more increasing in tensile strength compared to untreated starch or unreinforced filaments. Depending on formulation and processing, these compositional strategies are attractive for packaging, coating, and single-use replacement when mechanical performance approaches engineering threshold. Representative experimental material cellulose chitosan blends. Recent studies report tensile strength increases on the order of approximately 5 to 60% and similar increases in modulus when micro or nanocellulose is well dispersed within a chitosan and matrix, with the mechanical improvement depending strongly on interfacial adhesion and moisture content. Next point is smart testing system DIC motivation and capability. Traditional tensile testing record load displacement and calculate UTS from macroscopic failure. Smart testing augmentations full field digital image correlation DICs, high frequency acoustic emission AE and thermography and integrated high speed imaging enable detection of local strain heterogeneity, microcrack nucleation and failure precursors long before final fracture. This add sensitivity, reduces sample testing number via richer data per test and enable the construction of ML models that use sensor time series to predict UTS and damage states. Data fusion and benefits. Sensor fusion enhances sensitivity and sensor fusion enhances sensitivity and reduces false positivity. For example, a small AE spike accompanied by localized DIC strain increased by and thermal hotspot is strong evidence of a damage event. Application certification testing in process control for AM parts and accelerated material screening. Summary. No. Smart testing amplifies the system amplified data yield per test and enable earlier detection of failure precursors that are critical. They are critical for creating the database ML needs and for certifiable viable in process decision making. Summary. Physical mechanism that determine UTS. UTS is a microscopic manifestation of atomic bonding microstructure and defect population. Key mechanism include that control tensile strength include bond level, intrinsic bond strength sets an upper limit to theoretical strength, crystalline packaging govern slip system and critical resolved shear stress. These are the pictures for the dislocation materials of different materials, dislocation points for different materials. And next we are moving to microstructure heterogeneity and size effect. Grain size, Hall-Petch relationship. Small grain size increase yield and often peak strength by impeding dislocation motion up to a limit where other effect may dominate. Second phase particles and precipitate well dispersed nanoscale precipitate block dislocation or one looping and boosting UTS porosity surface flaws and notch sensitivity flaws lower effective UTS by concerning stress at if defect enabling parameters premature if fracture. This effect is pronounced in ceramics and brittle polymers. Next point is transformation and twinning mechanism. Transformation include plasticity and twinning include plasticity. In certain alloys including AGAs and steels, stress driven phase transformation or mechanical twinning contribute to sustained strain hardening and higher UTS well with retained ductility. The syringery is a modern material design target. These are the this is where digital twinning and twinning induced plasticity and interstitial free steels, and they are different elements and showing their ultimate tensile strength, metallic gases, crystalline nanomaterials, all of them showing their ultimate tensile strength. Next point is advanced or modern materials and route that alter UTS. HEAs. HEA are the closest to replacing high strength alloy in structural metal application where metallic strength and toughness are required. They can achieve GPA and GPA level UTS with appropriate processing, but cost or scale and compositional complexity remain challenging. Nanostructure, nano architecture lattice, nano-architected lattices offer an unmatched strength-to-weight ratio for a specific lightweight structural role and metamaterial application. They are most promising where ultra-light loading members are required, but manufacturing throughput and defect control limit mainstream use. Bio-based composites are rapidly improving and now can serve many packaging or consumer roles where biodegradability and reduced petroleum reliance matters. They are not competing with metals or on absolute UTS, but relative improvements make them visible substitute for some uses. Machine learning is a transformative enabling technology for faster design, process control and UTS prediction, but is only as good as the data and the physics aware features supplied. For narrow data sets, extremely high accuracy is possible. For broader generalization, uncertainty and quantification and hybrid models are advised. Next point is practical applications where UTS is essential. Structural engineering. UTS provide Structural engineering and aerospace. UTS provide the ultimate load threshold used in limit state design check and extreme scenario assessment. In aerospace, improvement in UTS material enable thinner skins and lighter frames. However, fatigue, fracture and toughness and damage tolerance are equally critical and design drivers. Next point is manufacturing quality and standardization. Tensile test is the primary acceptance test for raw material and qualifying process changes in additive manufacturing. Tensile coupon results are correlated and within the process sensors are used to certify builds. Standards define geometries and procedures for traceable UTS reporting. Biomedical implants. UTS is most used to ensure implants as and fixation devices have adequate ultimate strength compared to expected physiological loads. Implant designers consider UTS alongside elastic modulus, fatigue life and corrosion resistance to avoid stress yield and achieve reliable long-term function. Titanium 6, aluminum 4, vanadium UTS approximately 850 to 1100 megapascals is a common implant alloy for biodegradable scaffold material, also judging the tensile performance in vitro and after stimulated degradation. Evaluation and sustainable materials. UTS is first ordered screening metric for upcycled and bio-based materials. Improvement in reinforcement increase UTS and broaden viable application, but environmental conditioning and life cycle trades-off must be reported. Next, our point is testing and measurement, practice and enhancement. Standards and specimen geometry follow ASTM are ISO test standard for comparable UTS values and report specimen geometry, strain rate, or temperature and conditioning details. Advanced testing combine tensile test with digital image correlation for full field strain map with acoustic emission for early damage detection, and such sensors can increase insight into failure precursors and support ML driven prediction. Recent studies demonstrate effective DICs plus AE fusion for damage characterization. Limitation: UTS is a single what is the limitation? UTS is a single scalar that ignores rate dependence, toughness, and fatigue, all crucial in many import applications. UTS report UTS with supporting properties, yield, elongation, fracture toughness, SN data, and clear protocols and clear test protocols. Best practices include standardization, careful specimen preparation, environmental conditioning, and uncertainty reporting. And these are the sources from where I have taken the data for this presentation. Thank you so much. Allah Hafiz.